Well, welcome back to our course on system engineering. And for this lecture, we're going to be talking of systems engineering, or sometimes you could be just saying it's SOS engineering. And just to give a context where we are in the overall course. So we have the foundations that we gave a nice overview of what system engineering is. And then we went through the details of three parts of the life cycle: the front end, which deals with concept development, the development, which is the engineering development here, and then finally when it's in operation and the post-development. This is the last of three lectures that are dealing with that post-development stage, and then we'll be talking about some other things after we're done with this section. So let's go ahead and just get into some of the details for thinking of systems perspective. So for systems engineering, or SOS, or if you want to be thinking of systems engineering, it sometimes has the acronym SOSE, SOSI. So it's a specialty of system engineering that focuses on combining multiple systems together in order to accomplish an objective that a single system cannot achieve. There are some distinct differences between traditional systems engineering and SOSI, the system of systems engineering, and much of them stem from the level of control and insight into an individual system component that comprises these SOS. As SOSs are composed from a larger scale, they must be cooperation between multiple systems, management, funding, and operations as the SOS is being developed, integrated, and tested, and ultimately fielded. As the operational environment continually changes, existing systems may not be able to keep pace with these changes and either fall behind on their mission accomplishments, or worse, to fail their mission and become irrelevant. As it is prohibitively expensive to develop a new system tailored to the changes in the environment, we may opt to look at combining capabilities from different systems that will provide a complementary capability when joined together. However, the organization that is in control of the systems may not have the same common objectives as our system, so they would need to be convinced that collaboration would serve in both parties' interest. Defense systems come in mind when discussing system of systems, as there are unique capabilities within each service and the individual domains that systems were developed for specific missions. However, since the military forces are operating under one nation, some of these systems may be operating in close proximity to each other and would thus be available for collaboration together. Thus, the commanders can give the benefit of multiple systems without having to develop separate systems, but rather develop a common interface and procedures in order to reap these benefits. Well, let's think of some of the differences between the system of systems and traditional system engineering, many of which are related to the systems engineering method, where the traditional system engineering focuses on a single system and single managing organizations, and the SOS has multiple systems and organizations. So thinking of those differences between a system versus a SOS scope, a single system has a well-defined scope to encompass the individual systems, as well as the defined customers, stakeholders, threats, and other systems and organizations that the system may need to interact with. The scope will likely not change rapidly unless there is a change in the threat, users, or mission. The SOS scope will be variable, continually adding, modifying, or removing different constituent systems within the scope. As each of the individual systems mature in their individual life cycles, this may alter the SOS behavior and capability. Threats that mature may affect different parts of the SOS, where some of the systems may be more vulnerable to the emerging threats, and some systems may be more insulated and able to withstand advanced threat conditions. So we have 5 things. Well, first, for a scope, a single system has a well-defined scope. And so that would be different from a traditional for an SOS, where the scope would be variable, continually adding and modifying, as I mentioned. In terms of requirements, a single system will have well-defined formal requirements in order to accomplish its objective. SOS requirements would be less formal, and their requirements development relying on the individual system to develop their own requirements process and manage their capabilities. In terms of architecture, the individual system will have control over its architecture during its development, much like the requirements. For SOS architectures, their structure is less supported, relying mostly on the interfaces between the systems within the SOS. For testing, a single system will likely have one resource sponsor that will have access to their dedicated test train environments. On the other hand, SOS may have less defined items, such as who is in charge, who controls the resources, and who can handle the data. Finally, for acquisition, individual systems have an established acquisition process that is followed, while a SOS often do not have formal acquisition process, with the exception of a directed SOS. Okay, let's now think of the differences in terms of requirements. A single system will have well-defined formal requirements in order to accomplish its objectives that are clearly developed in accordance with the system engineering lifecycle process. These requirements have been developed with the assistance of users, stakeholders, other designers, and testers in order to satisfy the stated objectives and operate in a stated environment against stated adversaries. Of course, there will be some margin built in for these requirements to handle growth in threat capability or projected additional mission capability for the future system variants, but these are generally well known and agreed upon within the user community. SOS requirements will be less formal in their requirement development, relying on the individual system to develop the requirements, processes, and manage their capabilities development process. SOS will likely not have many formal requirements unless it is a directed SOS that has control over the management and funding of the individual system capabilities. So those are some things that will come into to bear there. So in this figure that we're showing, it provides an example of the legacy and newer systems when developing SOS requirements, where legacy systems will provide their capabilities and bring their system requirements. Newer systems will supplement the existing capabilities provided by the legacy systems and may provide either newer capabilities or provide redundant capabilities that may be needed by all systems. As indicated by the SOS domain, there could be capabilities that resides both inside and outside of the SOS scope. Let's now think a little bit more about the architecture, a system versus an SOS architecture. The individual systems will have control over its architecture during the development, much like the requirements. The architecture can help develop the functions and components that will ultimately result in the design of the system in order to accomplish its objectives. The architecture can also help shape the interfaces it will need to operate with other systems in the ecosphere. For SOS architectures, the structure is less supported, relying mostly on the interfaces between the systems with the SOS and anticipating that one system's output can be successfully input to another system and produce the desired result. Common interfaces or standards can be developed to ensure that the system has some level of interoperability, or the systems may receive some resources to modify their internal processes while accepting the common interfaces from another system. As these systems are continually maturing and upgrading, the entire SOS architecture may need to be continually updated to reflect these capabilities, and in some cases may need to retain some backward capability in order to continue to operate with the existing system. The figure we're showing here, it provides an example of new and legacy systems when developing an SOS architecture. So some interfaces between the legacy system may already exist. Other interfaces may need to be developed between existing systems. As the newer system is introduced to the SOS, the interfaces to connect to the other system will need to be developed as well. In terms of systems versus SOS testing, a single system will likely have one resource sponsor and thus have access to their dedicated test range environments. These ranges can be controlled and thus test units can be exercised to evaluate their capability that are under development. Test targets can be manufactured or reused from existing resources in order to evaluate the system performance. So for an SOS that contains multiple systems, the first question may be who is in charge of the SOS test? If there are multiple organizations and services, and who's in charge, who controls the data, who pays for the test, who determines the priority of the test against the other scheduled test. And so there's a lot of things that need to be determined in that perspective. So that just gives you a nice figure to be thinking about how we're going to be combining legacy and new systems. So in terms of the acquisition, and then we'll be showing this figure, giving a comparison between traditional and system of systems engineering, that you can be looking over that while we talk about this. So for systems versus SOS acquisition, individual systems have an established acquisition process that is followed in order to clearly define the objective and the desired end product to accomplish the mission. The program office in charge of the system development has control of the resources to help shape the development of the system, and is able to apply resources when needed to develop the needed capability of the system. As many of the SOS may not have a formal acquisition program and process, the acquisition decisions are often influenced by the individual system program office needs as they are developing their systems and capabilities. With an acknowledged SOS, there may be some oversight and overarching guidance in order to encourage individual systems to develop their complementary capabilities that will benefit the SOS. So the table shows a comparison between traditional system engineering and SOSI, the attributes that can provide some insight into the differences in which the systems engineer should approach and analyze the enterprise. Okay, we'll have a figure for each one of these, and here is 4 different types of SOSs, and the textbook refers to a reference Dominant and Baldwin. Their research on the types of SOS yields 4 distinct types that can be described: the behavior, structure, and level of control. They are directed, acknowledged, collaborative, and virtual. Their SOS definitions are discussed next, and we'll have a graphic for each one. First, for a directed system of systems, directed SOS are built and maintained to full specific purposes. Operations are centrally managed to ensure goals are met. Although constituent systems retain their ability to operate independently, they accept that the normal operational mode is subordinate to the central goals. Examples can be found in metropolitan transportation systems. Although independently owned, constituent services may cooperate to deliver metro services. They must also accept considerable operational direction in order to participate. So the figure shows a summary of the directed SOS attributes. Next, we have the acknowledged system of systems. So an acknowledged SOS have objectives recognized by the constituent systems, a designated manager, and a dedicated SOS resources. Constituent systems retain independent ownership, objectives, funding, development, and sustainment approaches. Unlike a directed SOS, changes are based on agreed collaboration. Air traffic control is an example. Systems delivering managed and safe aerospace globally all recognize their shared goals, collaborate on best practices, and adhere to regulation and protocols. So the figure that we're showing here provides a summary of the acknowledged SOS attributes. Third, we have a collaborative system of systems. And so collaborative SOS comprise constituent systems that voluntarily choose to participate to fulfill some central purposes, which can evolve based on collaboration between constituents and SOS. An electrical grid is an example. Autonomous constituent systems produce, transmit, and distribute electricity to consumers. Unlike an acknowledged SOS, there is no overall directing authority. Constituent systems adhere to standards and regulations, but can negotiate individually to evolve rules and work practices. So this figure that we're showing provides a summary of the collaborative SOS attributes. And finally, fourth, we have a virtual system of systems. So a virtual SOS have no central authority, nor an explicit recognized purpose accepted by all. A virtual SOS can exhibit large-scale and emergent behaviors, but relies on the standard formats or protocols. The internet is an example. The Internet Engineering Task Force publishes agreed standards and protocols. Independent service providers can leverage these for news services or products. No management or governance is either provided or accepted regarding use, and there is no central purpose for all parties. And so this figure provides a summary of the virtual SOS attributes. So let's think of the attributes of the SOS in general. SOS may be described through a series of attributes that it will embody. We may be able to evaluate if a collection of systems can exhibit these characteristics. The textbook refers to Mayer from a 1998 reference, a seminal article to describe these attributes of SOS, and we'll list them here. They're on the chart. We'll talk about them. First, we have operational independence of individual systems. A system of systems is comprised of systems that are independent and useful in their own right. There's managerial independence of the individual systems. The component systems in a system of systems not only can operate independently, they can generally operate independently to achieve an intended purpose. For geographical distribution, geographic dispersion of component systems is often large. For emergent behavior, the system of systems perform functions and carry out purposes that are not necessarily associated with any component system, leading to behaviors that are emergent properties of the entire system of systems and not the behavior of any component system. For evolutionary development, development of a system of systems is generally evolutionary over time. Components of structure, function, and purpose are added, removed, and modified as experience with the system grows and evolves over time. So these provide the initial description of how SOS can be described. And so in addition to the Dahman and Baldwin reference in the textbook, characterization of the potential types of SOS. Other researchers have found that complex adaptive system principles may be applicable to the study of SOSs, where the interdependencies and complexities of the constituent systems may produce a SOS behavior that may be unpredictable from initial analysis of individual systems until it is operating in the environment. So one of the challenges to systems engineering, the SOS engineer will undoubtedly encourage challenges to the entire SOS as it develops throughout the entire system engineering lifecycle. Some challenges to the SOS may occur that are outside its scope, such as new threat development, changes in competitor strategies, or the user needs may change. Within the SOS, constituent systems may opt to leave the SOS, while other systems may join. Policies and interfaces to help describe how the SOS system work with each other may change depending on the individual system strategies. So the textbook has a reference, Ring and Mandy from 2005 that list other challenges to SOSs that could affect the overall performance. Adding additional systems will bring a larger scope as well as increased complexity, potentially not understanding how the entire SOS will behave with these additions. Adding additional systems may increase the chance for error as now the response surface has increased for both errors and malicious attacks that could ultimately affect the entire SOS due to the interdependencies. Adding additional systems, organizations, and users may introduce unfamiliar terms or cultures that may decrease the user's ability to spot an error or warning. Unintended consequences may also challenge the SOS when one system makes a change and inadvertently affects the rest of the SOS. This may be to ignorance of how the other systems will be affected, or the error in calculation on anticipating how the other systems would be affected, or only in the system's self-interest. Keening and Katrina, 2011, another textbook reference, postulates other challenges to the SOC, System of System Engineering, in order to distinguish it from merely an extrapolation of traditional system engineering. Approaches and thinking need to adjust to account for evaluating the SOS holistically from multiple perspectives. This holistic view can be expanded from a purely technical aspect, but it also includes human, social, policy, organizational, and managerial aspects to analyze and develop the SOS concept. An increased level of technical rigor should be emphasized on the methods and applications to understand the system of system problems and interdependencies. Increased emphasis on other approaches such as psychological, axiomatic, and theoretical can also supplement the technical methods in analyzing and advancing the SOS field. Finally, better definitions of what a SOC should be responsible for, should know about the SOS, and what qualifications they should possess should also be explored. So the things that we have listed here on the slide, let's talk about them one at a time. Who's in charge? As expected, when multiple organizations collaborate on a single project, there may be potential for tension on who will lead the effort and who will follow, particularly when these organizations' systems capabilities are showcased as important objectives. In lieu of a directed SOS, there may not be a clear organization that will lead the effort. So some may point to systems that are performing the majority of the activities within a particular scenario or mission thread that should be leading. Others may point to systems that are performing the most critical activities or interactions, are who should be in charge. The amount of resources and or funding may also be also trying to determine who should be in charge, as they are shouldering much of the financial burden. Then we have to be thinking about interfaces and upgrades. As each system will continue to develop on its own schedule, there will be improvements in the individual capabilities, but this may or may not translate to improved SOS capability. As these systems are upgraded and improved, this may also pose challenges to configuration control for the entire SOS, which can be problematic when testing the entire SOS or planning or for development based on the assumption of the SOS configuration. If these upgrades are not backward compatible with the legacy system interfaces, then a local improvement in one system may cause significant degradation to the entire SOS. Communication of these planned system upgrades and roadmaps should be conducted frequently so other systems can plan for these changes and adjust their interfaces accordingly. Finally, we have interoperability. Initially, interoperability may focus on the technical interchange of data and formats in order to have the system accept inputs from other systems and send outputs to other systems. Understanding and solving these technical challenges may suffice for initial operability challenges between systems, particularly when new systems are introduced to the SOS configuration. However, the purely technical interoperability may not be the only challenge, as with the case with military systems or different services. Their systems may operate with different procedures or interpretations of information received. Thus, this lack of interoperability may cause correct technical information exchanges to be meaningless in terms of overall SOS performance. As with the interfaces, communication between all partnering organizations within the SOS should help to understand the differences in terminology as well as the expected performance. All right, well, let's finish up with a summary review of what we talked about in this lecture, in this chapter. First of all, the systems of systems engineering, the system of systems, SOS, and if we add engineering, system of system engineering, SOSI, is a specialty of system engineering that focuses on combining multiple systems together in order to accomplish an objective that is a single system cannot achieve. So what are the differences between system of system and traditional system engineering? There are several differences, many of which the traditional system engineering focuses on a single system and single management organization, and the SOS have multiple systems and organizations. In terms of scope, a single system has a well-defined scope to encompass the individual systems, whereas the SOS scope will be valuable, variable, continually adding, modifying, or removing different constituent systems within the scopes. For requirements, a single system will have well-defined formal requirements in order to accomplish its objectives that are clearly developed in accordance with the system engineering lifecycle processes. The SOS requirements will be less formal in their requirements development, relying on the individual systems to develop their requirements, processes, and manage their capability development process. For architecture, the individual systems will have control over its architecture during its development, much like the requirements. For SOS architecture, the structure is less supported, relying mostly on the interfaces between the systems within the SOS. For testing, a single system will likely have one resource sponsor and thus have access to their dedicated test range environments. SOS may have less defined items such as who is in charge, who controls the resources, and who can handle the data. Then for acquisition, individual systems have an established acquisition process that is followed in order to clearly define the objectives and the desired end product to accomplish the mission. SOS often do not have a formal acquisition program and process, with the exception of a directed SOS. In terms of the types of SOS, there are 4 types of SOS that have been defined in this lecture, in this chapter. We talked about directed, acknowledged, collaborative, and virtual. We had a figure for each one of those and the attributes. What are the attributes of a SOS? So there are 5 things that have been pointed out by the reference that I mentioned before, Mayer. Operational independence of component systems, managerial independence of component systems, geographical distribution, emergent behavior, and evolutionary development. And finally, for challenges to system of system engineering, some of these challenges include who is in charge, interfaces and upgrades, and interoperability. Okay, thank you very much. That's going to end it for this lecture.